As you're ready. Yeah. Hi, everyone. Sorry for the delay, and thank you for being here. Thank you to ICM for hosting us tonight. So tonight we have two very talented speakers, and we are very happy to have two talented women speaking tonight, Marine and Marie-Constance. So I let Marine, both of you, present a bit about yourselves before your presentation. And thank you. And thank you so much for accepting to participate in this meetup. So the first, there are going to be a couple of words about PyLadies and ICM. Then we have the first talk, Turning Your Data and AI Algorithm into Full Web App in No Time with Python by Marine Gosselin. And then Improving Non-invasive BCI, Contribution of Open Source Software Tools by Marie-Constance Corsi. And then after that, we have the cocktail session and networking. So a few words about PyLadies. We are an international community focusing on Python and related tech for women and friends. So it's, as you can see, is open. And if you are interested to give a talk at some point, please contact us. And is organized by volunteers, myself, Maria, and we have Maud, which are connecting by remote and organizing actually the broadcasting by remote from Aix-en-Provence. So our code of conduct is that be respectful and kind to each other. For more information, please visit the code of conduct on our website. And feel free to reach out to us in English or French. If there is anything that you see is bothering you, feel free to reach us, and we make sure to handle it. So our meetup usually is hybrid. We broadcast live, and then you can find the videos on our YouTube channel. And you can follow us on the Slack, Twitter, and YouTube channel. And on the Slack, if you go to slackinpyladies.com, City Paris is specific for the information related to PyLadies Paris and City of Paris. And then we are always looking for speakers, venues, and sponsors to provide goodies. So if your company or you are interested to give a talk, or your company is interested to host us for a talk, let us know. And very important thing, JupyterCon 2023 this year will be in Paris, as the Cité de Sciences is a really good tech conference, and PyLadies is a community partner, and we encourage you to look it up, register for tickets. We also have a scholarship open, so feel free to check it out. And as part of the organizer, we're trying to really make a diverse set of talks and interesting talks, so we are excited about it. So hope that you will be excited to join as well. And one more thing, Friday night, we have an online event organized by Our Ladies in Munich and Our Ladies Paris. And this is an online event, is a talk by Erin from H2O on AutoML. So if you are interested to know more about AutoML, you can join that meetup, which is fully online on Friday night. Okay, so that was for PyLadies Paris. Now I give the floor to, just let me share the screen. Okay, I don't know now, but perfect. Yeah, okay.
Thank you very much. Yeah. So thank you for being here. We're very pleased to host a meetup. In fact, it's our first tech meetup ever. We host at the Paris Brain Institute. So I will just take 2 minutes to explain what is this place you are and what people do in here. So the ICM, Institut du Cerveau et de la Moelle Épinière, in fact, is an institute, a private institute, but non-profit. It's a foundation dedicated to research on nervous system and brain, and also all disease, neurodegenerative disease of the brain. So we are in the hospital because we are really integrated with medical teams. And it's a structure when you have independent research teams, so 25 today, working on different areas of brain research. You have also a lot of people to support these research teams. We have what we call core facilities. It's microscopy, DNA sequencing, MRI. Okay. We have classic support services like the IT department, which I'm part of. And we also have startups incubated by the institute. So the figures, you see it here. We are more than 700 people from 40 nationalities. And we have a lot of scientific publications and patents also. So what are people here working on? We have 5 main research areas. So I just put them here. Some people are working on really with a microscope and cells and DNA, etc. Some people are working with patients coming here to participate in clinical studies. And we have also a lot of people here in the institute doing computational modeling, scientific computation, and that's why we have here a strong Python community. That's the main language I think people use in research. They also use R a lot, and sometimes other languages like C or... Well, that's it. So if you have any questions, but if not, I give you back.
Okay, so now I leave the floor to Marine, our first presenter. Okay. Let's go. Okay, so hi everyone. Today I'll be presenting how to turn any data, ML, AI algorithm you do into a fully fledged web application in no time with an open source library called TyPy. Just to present myself, maybe just quickly. So my name is Marine. I used to be a data scientist for 5 years. I worked in retail and food services subjects. And then for 4 years, I worked for a French bank and I did some fraud detection and prevention for payments. And today I'm a newly developer advocate for TyPy. So it's been a couple months and I really enjoy having this technical side as well as the community aspect that I really enjoy. Okay, so before presenting what TyPy is, I'll go back to why TyPy exists and what it was trying to answer. And basically, it starts with saying that data scientists have everything they need to build their ML projects. So from ETL, data handling, you have NumPy, you have pandas. For algorithms, you'll have everything from scikit-learn, for machine learning, and you'll have Keras for neural networks. And so you end up pretty quickly with an exposed model. But this exposed model, is not usable by the end users and is not industrialized, can't be industrialized as such. Gartner actually says that 85% of these pilots don't become projects. So some of the cases, it's because the pilots are not good enough, but most of the cases, it's actually because there's a gap of having this exposed model and actually putting it to a project.
because the data scientists won't have the resources to do it, you'll need maybe to invest in like someone that knows JavaScript or invest in those kinds of resources that the data scientists won't have. So basically, our founders wanted to give all the tools to the data scientists. And the founders of TypeI are actually very experienced people that work from Java. And when they worked this step to Python, they looked at all the libraries that were available, and they thought there was a gap in everything that would be front end and back end of creating a web app. So basically, TypeI helps any level of Pythonistas create a web app, basically. There are two models in TypeI. You have TypeI Core and you have TypeI GUI. Both of them you can use separately. But of course, if you want the most complete application, you'll have to use both of them together. For example, you could use TypeI GUI if you just wanted to do some dashboards for data visualization. Let's go a bit further now, and we'll look at TypeI GUI. So TypeI GUI allows you to build powerful web apps. And remember I said it was important for us, for TypeI, to make this accessible to any Python developer, Python user. So we really focused on something that would be easy to code. So how TypeI works is basically with augmented markdown. So you'll see here when you create your page, everything basically that's in quotes will be what appears on your web app. We also have the TypeI objects that we made as simple as possible. So here you have a TypeI object that basically takes your Python object with your data here, and it'll create a charts with some parameters. And because we wanted to make sure, for example, data scientists that use a lot of notebooks would be able to use it, we made sure it was compatible with notebooks. Easy coding doesn't mean less features and less complete of a solution. So we wanted to make sure we would cater to all of the users' needs and business use cases. So for our charts, we have an integration of Plotly charts. So you have a dozen of them. You can find them on the website. We're actually working on an API for any person, developer, to be able to integrate yourself, any graph, to make sure this is as customizable as possible. We also have our TypeI visual elements. So you'll have everything from sliders, drop downs, toggle, everything to make your application as interactive as possible. And so talking of interactive, we really worked on this interaction, and we have callback functions that are integrated. Other interesting features we have is that it can be multi-user, which is a feature I think we're first on, or we really try to focus on. We allow multi-page, we have custom layouts, and we're working on a CSS layout to make it easier, but it's also fully customizable. We have asynchronous and asynchronous mode. So synchronous is default. Asynchronous would allow you, for example, if you had a very large execution going on, it would still load your application instead of just having a blank page. It would still load your application, and you'd be able to still use it while it loads, basically. And then finally, there's this smart feature that I won't explain now because I'll show you in the demo right now. So for the demo of TypeI GUI. So let's do our little application. So TypeI is basically pip install TypeI. Here I'm importing GUI, and then I'm creating my page here. I'm opening the markdown, as I said. Everything that's going to be here is going to be my app. I'm doing a demo for PyLadies. This is going to be a title. I'm going to do a subtitle saying what we're doing. GUI. And then there's no autocorrect for my mistakes. And let's say I want to add like my parameter and then a number that I define. So I'm going to define my object here. Parameter, let's say value 10. And I'm going to start integrating a very simple typei object. So all typei objects have this format here. So you have the auto completion. Here I just want my param to come up, and it's just text, and then I'll close it. And now let's just page. So this is my page I'm running, and run. Okay, it's taking a lot of time. Okay, maybe the internet's. So here you have it, the small first app we have with my title, subtitle, and my little parameter that I created. That took literally 2 seconds. Now for maybe something a bit more complex. Well, still not very complex, but let's look at the interactiveness I was talking about. So here again, we have everything we defined that'll be on the web app. So again, my param here, and then this will put in italics. Here, I'm inserting a slider. So it's another typei object. Slider here, the default value will be my param, and then I'm defining a minimum maximum value for my slider. And then I'm defining a chart that will take on this Python object here, and that will be a line chart. So just to explain what the chart will do. So it's basically just a linear function that decays over time just to have some data. And then here's my function that will recalculate the linear function each time I change the slider value. So let me run this to show you guys. There you go. So here, each time I move it, so it seems it's very slow, but you should see the, yeah. So it moves each time I'm going to move it. And now, I don't know if you remember, but I talked about a cool feature that was called a decimator. I think the name is really cool. So the decimator, what it does, so it's a function created by typei that wanted to answer big data and graphical representation that have difficulties in Python, because if you have too much data, it'll basically just crash. So the decimator is a function that will remove the points that least change the shape of the graph. And it's really interesting because it keeps the value you want of the graph. So I hope it doesn't take too much time. And so we'll have the first graph. So I didn't put too much data because I didn't want it to crash. I wanted to show you the difference between both. The first graph will actually have around 11,000 points. And then the second graph with the decimator, which is just a function in typei, will have around 500 points. So you can see here, it does have the same shape in the both. The decimator function works a lot also for clustering, for example, showing clusters. So it's pretty interesting. Now, let's go to typei core. There we go. So typei core is allows you to build is a tool that allows you to do simple and powerful pipeline orchestration. So like a lot of pipeline orchestration tools, it allows you to do task scheduling, execution, as well as parallelism. But because typei was developed working with a lot of big companies and real life business use cases, we did find interesting to integrate other features. So the first one is scenario management. So a scenario is basically pipelines or multiple pipelines in which you'll change some parameters, basically. So this is a really strong tool for comparison and really interesting, for example, for end users if you wanted to compare cycles or things like that. You have some smart features like caching and data scoping. Caching basically won't recalculate something that's been calculated already. So if you have a pipeline with two tasks, the first task being filtering and the second task being separating data, for example, you run it once. If you run it twice, you change the separation task. You don't change the filtering task. It won't recalculate the filtering. So this is interesting for calculation times. Data scoping also is an intelligent feature that allows you to share data between pipelines. So this helps on data at disk space. Cycles is also a feature that's pretty interesting because it saves scenarios based on cycle in specific spaces. So it's like an organizational and allows you to compare behind. So for companies that work a lot of cycles, we'll have to do the same execution every week. This is very interesting, and they'll have it in bins and be able to compare then when they're ready and when they want to bring them out. Because we do work in real environments and real business use cases, versioning was really important. So we have 3 modes. We have experiment mode, we have development mode, and then when you're done, you push it to production mode. And then finally, we have a brand new feature that actually came out in our release that is 2 weeks old. That's called TypeI Studio. So TypeI Studio is a way to create your pipeline with an editor in this way. So it's basically drag and drop. How it used to be done is with a very simple code, but it was still coding. You can still use just coding, or you can use TypeI Studio, up to you. But we, again, wanted to make it as simple as possible. Now, again, some demos. So we'll create new configuration with TypeI Studio. Yeah. View, okay. Is it this one? Is this better? Okay. Cool. So let's create our configuration here. So configuration is here in the TOML file. There we go. This is, so TypeI Studio is an extension on VS Code. So you can create your TOML file. If you don't use VS Code, you can just then save your TOML file and bring it back up to notebooks or whatever. So I'll open it in this view, and you can see here that this is TypeI Studio. I'm going to do a very simple, basic pipeline where I'm going to have an input. So you can see, so it creates my file. My input here, so I have a value of 42. Then I'm going to create my task. That's, I'm going to double this number. There we go. So to get the function, I forgot. Let me show you. So I have another code here that's going to allow me to run my configuration once it's done. And here I also put the function that I want to put in the pipeline. So let's go back to the pipeline. And then I have my function here, double. Then I'm going to create my output, link them. There you go. And this is very basic, but this is my pipeline. And very basic. Again, this is my scenario. That's for the purpose of showing you guys. There you go. So here we have it. This is our first scenario. So once we're done with this configuration, we just have to load the configuration. So I created the same thing, but here I'm loading the configuration I did. I'm then just putting it as a configuration of the scenario I created. So this is the TypeI function to run it. I'm creating the scenario, submitting it, and then I wanted to print the value of the task. So it should be 42 times 2. Yeah, so here it says the job here is completed. Value at the end of task is 84. There's an option in here that I told you about, which is the caching. So it's here. And basically, if I run it again, then it won't calculate it again. So that's it for this quick demo on TypeI Studio. Maybe just to show you if you don't want to use Studio, this is what it looks like when you configure it yourself. So it's still pretty small in code and pretty easy. Depends on what you prefer. There you go. So now I want to show you some use cases and some web apps that are a bit bigger and a bit nicer, just to show you the potential of TypeI. So the first application I want to show you is churn classification. I think this one is really interesting because a lot of, I guess you guys and myself included, have done some machine learning models, and those exposed models we talk about. And I think it's a cool way to see how you could show it off to maybe if you're a student, to your teachers, or even to clients. So I'll show you this one, which is churn. So we have a first tab here that's just basic data visualization. So this could be really interesting if you have to do your EDA, for example, and just to like, once you look at the results, just come back easily to the data you have. In this case, it was comparing a baseline model and the machine learning model. So here you can compare both baseline. This is the feature importance, so super interesting, and a lot of clients, for example, do want to see this. So it's interesting to see. You'll have the metrics here that you can compare to both, and then you can bring up, if I press on this, the ROC curve. Here we have another tab that shows some model comparison. That's just a basic graphs here between both, just to have a clear idea. And then finally, we have a tab that shows the different data sets that we use if you wanted to like show them, have an idea of what we're working with. Yeah, so I thought this example would talk to a lot of people. The second use case I wanted to show you guys maybe a bit more real life and this time usable by the end users, basically, is production planning. So I'm just going to create a new user. There we go. I'm not going to do it. Not going to do it. It shows you're listening, so that's good. Okay, and this is also interesting because it shows a bit more about the scenarios. So we have the first tab. So basically, it's a production planning of 2 products, I think, a chair and a table. Here you have the data that was used. So this is not machine learning, it's just an optimization and modelization. And we have here the prediction, the forecasting of the demand for product A, product B. So product B, we can see, is pretty flat compared to demand, the demand of the product A. Product A we see is very different and variable depending on the month. So I guess for people looking at this, they would be like, okay, I have to make sure my capacity work and my production is as good to be able to meet this demand. So what the end user would then do is look at the scenario. So let's start and create our first scenario with, let's say this is our capacity right now, and we want to see what it would do. There we go. So for this capacity for product A, you can see this demand curve that we saw just before. In red dots here, we have our maximum capacity. And then in blue, we have our production. So we can see that this is a really interesting graph because it shows us we actually produce a bit more than the demand here to make sure we meet the higher demand, in this case, where our capacity is lower. Let's say now that we know that our capacity is going to be a bit lower in the next days, or we want to maybe decrease our stock expenses. And let's make a new scenario. So we can see that the maximum capacity here is lower, and we can see that the production actually flatlines a lot quicker to make sure we meet the demand here. So this is really interesting for end users to use and take their important decisions behind and bring out KPIs. You can choose here which scenario you prefer. Let's say I prefer first one, so I'll make this one primary. Now let's compare them a bit better. For example, on the cost comparison of both scenarios. So for the stock cost, of course, if we have a capacity that's lower, we have less stock. So makes sense that scenario 2 is cheaper on that side. And then for the back order cost, makes sense as well. If we have if we flight line easier and we have a smaller capacity, that the back orders will be more expensive because we'll have to order more beforehand. There you go. And then here you have some cycles we compare and just the database that we were looking at. So that's it for me. I hope you're excited, and I hope you'll try TypePy. And if you have any questions, please do.
Thank you. That's really interesting. I have a question. How do you deploy to production? Can you host it on your server? Or?
Yeah, so we host it on a server, and we have a cloud offer as well, if you want it. Yeah.
In the website, say a framework.
I've never seen it, but I'm sure if you have the time, you can.
I have a question.
Yeah.
So continue our questions. So you have, since you have the packages open source, I assume that they can, a user can develop.
Exactly. Yeah.
And then I have several questions, but this is the second one. So for the second scenario that you explained, production planning is a very interesting scenario. And how is the connection to the database? So because I assume there's changing scenarios and changing the information, directly the data is saved in the SQL database, or?
That depends. You can plug it to whatever you want. I guess for this, it depends on your infrastructure, but you can put TypePy above anything you have. Yeah.
Okay. Any other question?
How would you compare to the Plotly library that I've heard before about that seems to do something a bit similar, which is having Python code and exporting to a web app?
There are a lot of different, like all the smart features I was talking about. So if you're just talking about the GUI, there are a lot of smart features that we talked about. I think we're actually working on a benchmark with a lot of other of our competitors. We can't really say that it's open source, but just to see in terms of performance how it works and how it. But I would say Plotly doesn't work multi-page, doesn't work multi-user. Is not as performant. Yeah.
Could this be integrated with Jupyter?
Yeah. Yeah. It works with Jupyter Notebooks. Yeah. Well, if you have any more questions, you can ask me as well later on. No problem. Thank you.
Thank you.
Okay. So good evening, everyone. My name is Marie-Constance Corsi, as you can see on this first slide. I'm currently an Inria research scientist here in ARAMIS team within the Paris Institute. So today I will present mostly, I'm trying to present first, of course, our research, but I'm trying to also illustrate our points with several tools we're using in our lab with also very practical examples. So my main research consists in trying to improve brain-computer interface, and we'll explain more into this what is actually a BCI. But in our case, we're more interested in non-invasive BCI, and we're trying to improve it by several ways. So we have like two parts. The first part will be more machine learning oriented, and then it'll be more neuroscientific, neurophysiological oriented. So first, what is a BCI? A brain-computer interface, or BCI, consists in trying to translate brain activity into commands for control, for instance, to try to control a real object, such as a wheelchair, for instance, and or to communicate with relatives. So you have different kinds of paradigms that can help you in trying to control and or to communicate with somebody else. But it's kind of blurred definition because it can be like a black box. So now I'm going more into detail more in this. So we have like 4 main steps just to build your own BCI systems. The first one will consist in trying to extract brain activity. And for that, we have different tools. In our lab, we are more interested in non-invasive tools, but we can also imagine other kind of modalities. So, of course, you have plethora of tools, but to be actually purely honest, most of the time, people are using electroencephalography, EEG, corresponding to this kind of setup, in which you will extract and record the electrical activity generated by the brain through a cup. And so we'll put some gel just to, depending on the device, but still you will record the electrical activity and you will translate into commands for the BCI. There are other tools you can use, like near-infrared spectroscopy, functional fMRI, and magnetoencephalography. But most of the time, most of the research actually rely on EEG that is portable and quite easy to use. So once you have recorded brain activity, you want to extract the most relevant information to be able to detect the subject's intent. And for that, it corresponds to the features extraction. Depending on your paradigm, you can be interested in different types of information, like temporal information, like time series, or power spectra, for instance. So here, to illustrate my point, I just wanted to take a specific paradigm that we're using in our lab, corresponding to the motor imagery-based BCI, in which you're going to instruct the subject to perform a motor imagery task. So it corresponds to imagine, for instance, like a grasping movement of a right hand, this one, and you compare it to another task or resting state, for instance. So here we can imagine have 2 tasks to be discriminated, motor imagery and rest. So our mission is try to discriminate this task. So you first going to use EEG information corresponding to this kind of line. You have 1 line per electrode, corresponding to the time series recording through the electrode. And from this information, we'll be able to estimate the power spectra, so like the energy of the signal. And we can plot like this kind of representation, like a subplot, just to show you here that you can have different, let's say, power spectral amplitude depending on the task. So for a given electrode, it calls C3, located over the sensory-motor area, we can observe that we have some changes in terms of power spectra depending if we're in the rest condition or in motor imagery. So the point here is try to take advantage of the power spectral modulation to detect the subject mental state. If it's not clear, let me know. I can, okay. Otherwise, I can talk by myself. It's quite boring. So, so we have these features, in our case, power spectra, and then we're going to classify. So to use different algorithms. It can be linear discrete analysis, support vector machine, or more sophisticated methods. And we are going to provide like an output, like binary in our case, 0 or 1, 0 codes for rest and 1 for motor imagery. And based on this information, we can provide to the subject an information called feedback. So in our case, it can be the position of the cursor that is moving in real time. So for instance, in our experiment, we can imagine that the aim is to hit this target, and through the burn activity, we are going to control the position of the cursor. Is it clear? Okay. So that is just behind the magic of BCI. So as you can see, it's quite interesting, of course, but we have plenty of applications, but still we have one main limitation, because the current BCI device failed to detect mental intention in about 30% of the users. It corresponds to the BCI inefficiency. It corresponds mostly on the high inter-subject variability in terms of performance. So even after several training sessions, some subjects cannot control the BCI system. So it's a huge problem. So one of my jobs is actually to try to find ways to improve and to address such issue. So for that, it's important to have in mind that it's a tale of two learners. I mean, when you try to control the BCI system. Of course, we have the machine. And historically, the BCI domain was mostly developed by engineers. So we were mostly focused on the machine-centered approach, in which we're trying to improve the signal processing steps by, for instance, removing artifacts, and also by developing more sophisticated classification algorithms to better detect the subject intent. But more recently, there is a growing interest in trying to take into account the subject specificity by several ways. For instance, you can take into account human factors and cognitive profile through questionnaires, for instance, but also by trying to identify potential neurophysiological patterns of BCI performance and training. So, in other words, through the information you can extract from the EEG, potentially we try to predict the ability of learning how to control the BCI system. But they're not flawless, in the sense that the first case, most of the time we are using only EEG, meaning that we have to face a low signal-to-noise ratio. And in the case of the user-centered approaches, they're quite new, meaning that there is a lack of reliable markers because we don't have so many data sets that we can actually use to extract such information. So in a nutshell, the neural mechanisms that could underlie the BCI learning remain poorly understood. So we do not know actually what's going on when one subject is trying to learn how to use the BCI system. So in our lab, we are trying to consider different approaches and mostly multimodal, but also we're trying to identify potential markers of BCI training to better understand and to try to improve the BCI trainings by trying to develop tailored programs. So in the first part of the presentation, I'm going to present more about some information about machine-centered approaches through like more machine learning methods. So in the literature, you have some tools to improve signal processing steps, but also to try to adopt some hybrid and multimodal approaches, meaning that the underlying idea is try to enrich information to better, discriminate subject mental state. So you enrich by adding more information through different modalities. So I'm not going to explain everything, but just to give you a hint about what is possible to do, we recently tried to combine different modalities, electroencephalography and magnetoencephalography, so the electrical activity and the magnetic activity obtained from the brain. And we combine them in order to be able to improve the classification performance. So just to give you a hint, it corresponds to the fusion approach here in blue. And what we observed is a significant improvement of the area under the curve with the fusion approach with respect to the state of the art that is EEG in the BCI domain. So it is a first idea, but why not make it more generable by perhaps using more diverse features. In our case, with motor imagery, we are most of the time focused on power spectra, but why not using other features that could be relevant to improve the classification. So, as I mentioned before, in the case of multi-imagery BCI, we are interested in power spectra. So, just a recap, so from the EEG information, you're going to estimate the power spectra, and you can take advantage of this kind of modulation of the power spectra to detect subject intent. But the point is, here we are only using a local measurement of the brain activity. We're not going to take into account the interconnected nature of brain functioning. We're not going to use the communication between brain areas. So why not using brain networks as a potential alternative features or complementary features? So for that, we are going to, again, use information from the EEG, for instance, and then instead of using power spectra, we can imagine to use connectivity matrices. So here, in each element of the matrix, it corresponds to an estimation of the interaction between two electrodes or two brain regions. And from that, you can apply different methods to binarize it to obtain the network. The easiest way would consist in simply applying a threshold, but it's not like the best way, but it's just a way to obtain a network from that. So for those who are allergic to math, no worries, not look at the great stuff. Just to give you a hint about what we can do by trying to combine different approaches to improve the classification performance. So in the BCI community, there is a growing interest in using geometric methods based on covariance matrices. Why? Because actually they provide good generalization, they're robust towards noise, and it actually, from a purely empirical point of view, gives very nice classification performance. But in parallel of that, in our lab, we are super interested in trying to use functional connectivity estimators as potential features. So in a former work by Titina Katai, a former PhD student of our lab, she proved that functional connectivity can provide insights about task performed by the subject while they're performing a BCI task. So potentially it can be interesting to combine both of these approaches to take advantage of the information they provide. So our hypothesis here was to combine functional connectivity estimators with geometric methods to improve the classification performance. So why? Because actually by using functional connectivity, you can also consider the subject specificity by considering the interactions between brain areas, and because through the geometric methods, you can improve the robustness. So here we actually adopted an ensemble learning approach. So from the EEG signals, you can estimate the covariance matrices and then project them into a manifold to afterwards propose a prediction, like a classification. You can do the same from the functional connectivity estimators, and then through the ensemble learning approach, you can provide a final decision. So it's like one level classification with covariance matrices and functional connectivity, and second level through the ensemble learning approach. Yes. I wanted to mention actually as an open source tool we are using in our lab. I would like to mention WebBB. I put you here the QR code to their website. It's actually super powerful. I'm not paid by them. I need to mention that because these two actually provide super nice functions to do some benchmarking to actually be able to compare different BCI algorithm pipelines. Because most of the time, not most, but some papers, they only mention the accuracies, but there is not like a real comparison with the state of the art. So from a purely methodological point of view, it's always nice to have these kind of tools, even for students to learn how to conceive their own pipelines and to compare them with the baseline and with state of the art. Another element that this tool also give you access to publicly available EEG datasets from different BCI paradigms, so P300, motor imagery, and so on, and it's open source. So it relies on the use of MNE Python. I will talk about it afterwards. That is a very nice tool to pre-process, but also analyze magnetoencephalography and electroencephalography data. Of course, since we're talking about machine learning, it relies on the use of scikit-learn and on Perryman that enables you to use geometric methods for classification. So in our case, our approach called Vugon, if you're interested by the meaning of Vugon, I will explain it later on. It's a Corsican name. But here, what we wanted, just to illustrate my point about benchmarking, instead of simply use our approach and trying to compare it with the state of the art on one data set, we tried to perform a thorough analysis on many data sets just to be able to identify and to assess meta effects. So just to prove that it's not like a one shot that actually works, but actually that provide robust results over high number of data sets. So here an example. We compare our approach with different algorithms for two classes case, like it was right hand versus feet over 5 data sets, and then here we're measuring the meta effect. It's not super clear, sorry. Effect here. So each figure corresponds to a comparison between our approach, Vugon, and the one of state of the art. So it was CSP with LDA, for instance, or with SVM, or geometric methods. Here is a link also to our GitHub repository, so feel free to look at it. So in the end, okay, of course, it was nice because it showed actually that we could observe a very significant effect, in terms of, accuracy. We could improve the accuracy by using the Vugon approach with respect to the state of the art. So meaning that it's not like one shot, but this approach could actually improve the results in most of the cases for 2 classes, 3 classes, and also 4 classes, if I remember correctly, within session and cross session. So we tried to perform the analysis to make sure that it was replicable and robust. So enough about myself. I just wanted to do some demo to show you how we can use MobiB to perform your own pipe analysis. So I just put here like QR code to the binder that you can use afterwards if you're interested. But just to be sure that we're going to be on time, I'll let to show you a notebook. So I try to put as many references as possible, both for the different, I would say, Python package, but also the associated papers. So here we're going to use an open dataset from Schalk and colleagues, and we're going to apply our approach, Vugon, because I'm going some propaganda, it's important for us, and to actually use it for an open dataset. So step 0, we're going to import all the packages necessary for analysis. So as you can see, we're going to use different functions from MobiB, in particular for plotting, but also to compute and to perform statistical analysis between pipelines. Then here we're going to use MNE-Python to actually load the data and to get it into epochs or repetitions. So I think most of you know about these packages. And the Perryman is for the geometric methods to perform the classification. As you can see, we can find like common spatial pattern here, another tool for the classification. Here are the list of the features we're going to use, covariances, matrices, and coherence. And finally, of course, it learns all the functions to actually perform the classification and to estimate the performance. Then here we're going to define a class to be able to extract the connectivity-based features. So basically here it will consist in defining a function to calculate the functional connectivity based on the coherence from the Perryman package. So the most important parameters are, of course, the methods, the frequency, the mean, frec-min and frec-max, and the frequency sampling. Then, so I guess most of you are not familiar with EEG, so I just wanted to show you some examples that we can find from MATE. So here we are defining the dataset we are going to use, so EEG BCI. We are going to specify analysis between 1 and 2 seconds, if I remember correctly. And here where we're going to be focused in trying to discriminate two tasks, hand motor imagery, hands motor imagery, and feet motor imagery. Just for sake of, let's say, not too long, I will just focus my analysis on one subject, subject 7, and on specific runs. Then, it's really interesting, this point. And then we're going to define epochs. So an epoch corresponds to one repetition. So it will be like or hands motor imagery or feet motor imagery. So we have some information here. So if you're interested, just to show you. So in epochs, you have different information that can be relevant regarding the experiments, such as the channel names, so the name of all the electrodes. If there are different bad channels, everything can be interesting and relevant to perform the analysis afterwards. Here's just the list of the EEG electrodes that are going to be used for the classification. Yep, of course. Here, just to check that we have a dictionary in which we code like 2 for hands motor imagery and 3 for feet. And yeah, afterwards, if you're interested about the dimension of the data you're going to manipulate, you can look it afterwards. So just to give you an idea about the shape. Nice. It's demo effect today. Ah, no, wait. Let's try. Nope. Cool. Let's try this. I'm cursed. Perhaps I need to reload it. So I should. It works before. Okay, just one last time, just in case. Okay, well, never mind. It works, but not today. So simply, I just wanted to show you an example, some time series you can use. So it's like just information for each electrode. And here, if you want afterwards to play with it, you will be able to plot that the power spectra, either for all the electrodes or just for a subset of electrodes. So now, going back to the machine learning stuff, here we're going to define our pipelines. So we're going to use as baseline 2 pipelines based respectively on CSP. So we're going to combine CSP with SVM, so a command spatial pattern with support vector machine, and another method based on geometric method, so random geometry. Here we are going to define the list of connectivity features and covariance matrices we're going to use. And here is just the list of the different steps we're going to use to use our Rugon approach. So here we're going to first extract the features like covariance matrices and functional connectivity. Then we're going to project into the manifold. And from that, we're going to apply an elastic net. And here is just the piece of code to apply the ensemble classifier, again, based on elastic net. Here just to get the result. Just like, it's quite fast, but just to avoid like spending like 20 minutes, let's try if it works. Yes. So here's the result, at least one thing that is working today. So here is just to show you like the data frame you can obtain afterwards. So for each split, when you perform the cross-validation, you have like data sets and subject ID, the score, the pipeline, and the number of samples used to perform the classification. So you can see the list of the different pipelines we used. Here, it corresponds, it doesn't make sense here because we only have one subject, but once you have obtained the classification over all the subjects, you can perform more robust statistical analysis, and you can apply this function, and then you can plot the associated results. So we have 5 splits per subject, not many points, but just to give you a hint about the potential score you can obtain from one given subject. So here we have our approach, Vougon, with respect to the state of the art. So based on CSP plus SVM, geometric methods, and each of the connectivity-based features taken separately. So it was a little demo. Now, Now, in the second part, if I'm not too late, I just wanted to mention some additional information about another approach that can also be adopted, in which we're going to take into account subject specificity by trying to identify potential patterns of BCI performance and BCI training. So here, let's imagine that we're going to perform a BCI experiment in which a subject will be instructed to either perform a motor imagery task or to run at rest, depending on the position of the target here. It's like a Pong game. So here, my point is, instead of using to perform online analysis, we're going to use to collect as many data as possible and to perform offline analysis. You're like super obsessed by the video, I think. It's normal. So yeah, as you can see, that's not super easy. I mean, and as an experimenter, we are going to support them like coaches. But anyway, so here, just to show you, it's not easy at all, and it requires a lot of time to be able to control it. If you want to know all the backstage, let me know. I can give you more gossip details also. So yeah, so let's imagine I have collected all the data from a given subject, and you want to analyze it afterwards to extract potential markers. So I just wanted to mention a very nice tool called MNE-Python to pre-process and analyze EEG and MEG data, so electroencephalography and magnetoencephalography data. So we have different steps to do. First of all, I strongly advise all the people not going directly to conceive a super fancy pipeline, but first of all, to inspect the data and to understand better what's going on, because perhaps during the experiment, there was a specific problem that can generate some artifacts. So it's important to take the time for this first step. And by inspection, for instance, it can consist in trying to plot the power spectra, because you can spot, for instance, specific artifacts that can occur at specific frequency bands of interest. For instance, when you have the screen, you can generate an artifact at 60 Hertz. You have the power line at 50 Hertz, etc. Then you have the artifacts removal. In the case of EEG and MEG, you have different types of artifacts. It can be related to the environment, such as the power line, for instance, or physiological, one related to the cardiac activity or the blink activity, because you know that your eyes actually generate also electromagnetic activity. So we need to remove it. Then you will do what we call a source reconstruction. So you will combine both information from EEG and MEG and the anatomical information to be able to estimate the electromagnetic dipoles. I can strange names, but I'm going to just to try to estimate the location of the activity you're going to measure from the sensors. And then you can perform more advanced analysis, such as networks based on this information. I guess I don't have so much time, but just to mention this wonderful tool, I'm not paid by them again, but it's super interesting because it's quite complete. And again, they provide also tutorials. So for someone who is not actually, who is probably new in the domain, students, it's really nice because it's not just providing you some information about the function, but also some do and don'ts about processing the analysis. So you can do pre-processing, all the steps I mentioned before, but also they provide machine learning functions, encoding models, and data visualization. Sorry. I don't have them today, but still, I also have a notebook if you're interested by the main steps regarding the EEG and MEG signal processing steps. And I just wanted to illustrate this point. So let's imagine that you have collected data, you have performed all the analysis, but then what kind of information you can obtain, extract from that. So here we're interested in trying to identify potential patterns of BCI training. So first, we wanted to check that we actually observe the training effect. So the first thing consists in trying to actually to compare and to study the evolution of the BCI score over time. So in our case, the BCI score corresponds to the percentage of time in which a subject could control the BCI system. And from that, from the EEG we collected before, we could actually see very nice trends in terms of power spectra related patterns over time. I think I'm quite late, that's what. Okay, I thought I was. Okay, so just briefly from the power spectral information, you can perform analysis in which you compare motor imagery condition versus rest condition. So at the beginning, we couldn't observe anything because it was super hard for the subject to perform the task. But as time goes by, we can see that we can observe very nice a significant discrimination effect between the two conditions that were more localized over sensory-motor areas, which makes sense given the task performed by the subject, by the way. Then another way is instead of using the local information, you can again use functional connectivity and to study the evolution over time. So here, just main message like bluish as time goes by, but just main information is like you can observe, a functional disconnection occurring over time that can be a certain pattern of BCI training. So just for the record, this kind of representation called connectome is really interesting because each dot corresponds to a region of interest or brain area. So it's like from frontal here to occipital area, here corresponding to the left hemisphere and here to the right hemisphere. And each link codes for the significant change between the two conditions in terms of amplitude of the interaction between two brain areas. Or the t-values from the t-test, if you prefer. So you can also use specific brain network metrics as potential markers. So in our case, we use a node strength. It's like a measurement of how centralized or how a given node is can be a hub of communication. And such information can be used and can show some correlation with the amount of learning when one is trying to control the BCI system. Meaning, in other words, that such information can be used as potential markers of a training effect. Yes. Yes, and I also wanted to mention, because since we are here in Paris Institute, it's nice to see some clinical application. So one of the main clinical applications, the BCI system, would be stroke recovery and rehabilitation. So in our case, we know that after the stroke, we can observe some dramatic changes in terms of connectivity between brain areas. So such changes can be also used as potential patterns of recovery. So it is an ongoing project here, performed here at the ICM, in which we are following patients over 1 year through 5 visits. First, during the acute phase, 10 days after the stroke, 1 month, 3 months, 6 months, and 1 year after the stroke onset. And one of the aims of this project is try to identify potential markers of stroke recovery and to see if they can also predict some potential clinical scales, such as the motricity, for instance. So finally, these take-home messages. I just wanted to tell you that to try to improve the BCI system, you have different approaches. The perhaps more intuitive one would consist in trying to improve the machine itself by trying to develop more sophisticated classification tools, by trying to integrate different modalities, or perhaps think about different types of features. Then another approach would consist in trying to take into account subject specificity by finding new patterns of BCI performance and BCI training. But regarding this last part, it's really hard because even though you can find very nice correlations with the behavioral information, are they reliable? Because perhaps it can work with you on the data set, but once you're going to apply to another data set, it won't work. So it's like an unsolved problem at the moment, but I just wanted to mention very recent result we obtained with a colleague from Marseille, Paolo Sorrentino, in which we used another type of features based on non-linear dynamics, and we could observe that we can actually extract more robust patterns with respect to the power spectra. With power spectra, we could obtain patterns, but they could be detectable at the group level only, whereas in our case, it was possible to observe it even at the individual level, meaning that we can potentially decrease the inter-subject variability I mentioned at the beginning of my presentation that can be hard for the classification. With that, I actually thank all the colleagues from different institutes and you for your attention.
Any questions? Line maybe? Check.
Is the geometric space like a parameter space, or does it have to be like smooth, or can it be piecewise smooth?
Actually, one of the main advantage of using such geometric methods is that from the features you can average them, so you can manipulate them more easily than with the classical methods. If it's the question.
What is the geometric space you have?
Remnant geometry.
Yeah. I mean, what is the space? Is it the parameter space of your?
No, you don't have to tune specific parameters.
Okay, because when you say remnant geometry, it has to be smooth.
Mm-hmm.
And typically you have some piecewise smooth structure, and at the singular points you have some things localized around it. Something interesting can be localized.
No, in this case, it's not that.
And do you have can one simultaneously have amplitude synchronization and phase synchronization? Like you had a diagram.
Yeah.
With two kinds of synchronization. Can you achieve both at the same time?
It's a good question. For the multi-imagery, most of the time you're only focused on the amplitude, but now there's a growing interest to try to monitor them through the phase. But we, for instance, connectivity metrics based on the phase, and they tend to be quite interesting to potentially be complementary to the power spectra to improve the classification performance. So we cannot use them instead of the power spectra, but perhaps complementary to that.
Any other question?
Yeah.
When you speak about the connector with the time, so to compute this connector.
This fancy one.
Yes, this one. So what window of time you used for each connector?
Okay, so here it is a way to plot the result from the statistical analysis. So it was at the group level, meaning that, for instance, in our case, we had like 20 subjects. So for each subject, we average the connectivity estimators over all the trials, all the epochs. So for the multi-imagery on one side and rest on the other side. So we had like 20 estimators from each condition, and then we performed the t-test. But for each trial, we considered only the time window in which a subject actually performed the task. So when they got the feedback from the BCI system. Now when you have like the moving cursor. But of course, you mentioned, because you have an effect of the time window of interest for sure, depending on when you're going to estimate the connectivity, you're going to have the same results for sure.
Thank you.
I have a question. So I assume the experiment is well controlled. So federated learning to try later on other experiments maybe is a bit difficult, but do you see an approach to that? that you can really use that to increase your data size and increase the diversity of samples. And
Yeah, actually, we are struggling in trying to combine different data sets because, of course, we don't have exactly the same montage, meaning we don't have the same number of electrodes. Sometimes we don't have the exact instructions provided to the subject, so we have a quite high diversity. One way would be like to have multi-centric studies in which we have the same protocol for everybody, but in different centers, research centers. Can be a solution, but it requires a lot of time and some money. But it will be as the best solution. But even if you have the same protocol, you need to be sure they have exactly the same hardware system. Everything is the control. But you have now, from machine learning perspective, new approaches that tends to learn from different data sets through transfer learning, to trying to take advantage of the measurements of data to learn from different montages to predict another one. So there are some ways to circumvent it, but still it's better to have like a number of subjects and for protocol.
Okay. I will have a very general question. You show that it's quite difficult to understand exactly what's happening with the proper EEG. What is your point of view on the dry EEG developed by many companies, or just a few other?
I don't have, to be honest, real experience in that. From what I heard from my colleagues, so most of the time, they suffer from low snare-to-nose ratio. It's noisier, but sometimes it's better because, it's easier. From a practical point of view, it's like plug and play, and it can be nice, especially to, let's say, democratize such developments for students or outside the laboratory. It can be convenient and interesting. So depending actually on your scientific question and how accurate you need to be, perhaps it can be sufficient for you. It depends. It's like diplomatic answer.
Any other questions? Yes.
You mentioned that 30% of the subjects have difficulties to get BCI results. Do you have an idea about the reason why now?
Many reasons, actually. Actually, that's why I'm mentioning like two-tailed problem, because, okay, historically people said, okay, it's because of the subject, because it's easier, you can control them, for sure. But I think both of them. Of course, if you can improve the classification performance, nice, but there is also a lot of parameters related to the protocol itself. For instance, which kind of instruction you're going to give to the subject. Is it explicit, implicit? Are you close to the subject? Even the interaction between the experimenter and the subject can have some effect to the success of the protocol itself. Another, just a list of the parameters that you can play with. The feedback also. Depending on the kind of information you're providing to the subject, it can have an effect to the success, because too many information can increase the workload, but too few, wouldn't be super informative and wouldn't help the subject. So potentially all the steps I mentioned at the beginning of the presentation about the BCI can have a strong effect on the success of the protocol. So I'm sorry, it's like it's a really complex problem.
So did you find the same rough 30% even on the subject that you mentioned with the stroke? So it will mean that it's not a problem about the pathology in this case? So
in our case, actually, it wasn't a BCI itself, because we only asked the subject the patient to perform a multi-imagery versus stress. So we don't have, like, at the moment, a closed-loop system. So I can't answer at the moment. But there is a new project led by Fabrizio Di Vicofalani in which he's going to study that.
Generally, question, when we have signals going between different parts of the brain, are there like interference between the signals? I imagine they are passing through similar brain regions, or there may be the same set of neurons. So are the signals interfering with each other?
You mean between subjects? If you can
No,
observe
just
something?
like in one brain, like we have different interconnections. Right? as given in the diagram,
Uh-huh.
there are interconnections between different parts of the brain.
Yes, exactly.
So I imagine the signals are passing through the similar region, and are the signals interfering with each other, or can they just pass through?
You mean like physically or?
Yeah, physically.
No, he just like from, you like more my colleagues from the image processing, but here it's like more at the information from the signals itself. It's not like physically a path that can be built through the EEG. We're not measuring that from the EEG. It's more the electrical activity that we are going to study to potentially identify interaction between brain areas. So it's quite different, like physical, it's like functional activity elements.
Okay, thank you very much. So, I'm just gonna connect. On YouTube. Thank you for following us and hope you enjoyed the talks. One more time for the two speakers. And so now we have the networking session thanks to ICM. So please enjoy. And we have the venue here until 9:30. Thank you very much.